Hello. In this video, I will solve some exercises first on approximating the areas under curves, which we discussed in the previous video that the area under the curve is one of the fundamental interpretations or meaning of the antiderivative, right? I discussed theory and I walked through the content in this textbook in that video. In this video, let me first solve problems. Okay. Then, if time remains, I will see if I can continue. Okay. Some examples. I will go serially at the beginning and then I'll choose some problems later. Suppose an object moves along a line at 15 meter per second between 0 and 2. So in this question, they are asking us to draw the graph. Okay. And use that, to find the displacement of the object. So as I talked about in the previous video, the velocity graph, the time and the velocity, velocity on y-axis, the time on x-axis, we call the velocity graph, is a very good physical example for the concept of antiderivative, right? The velocity represents the derivative of a function, the derivative of distance function, and the time is the independent variable. So the area under that curve will be the distance. Okay, so the antiderivative of the derivative is the original function in some sense. Okay, that is the idea. Okay, so that is what we are going to illustrate here. Velocity is here, time is here. Velocity as a function of time. Okay, v of t. And then what is the graph? The first problem, of course, this is simple. The value is 15 meter per second from 0 to 2. Let's say 2 is somewhere here. Constant velocity, less than, so let's put an open circle there. And between 2 and 5, the velocity is 25 meter per second. Let's say 5 is here. Okay, now it's not exactly to the scale, but you get the idea. And what is the displacement? So the concept was we should find the area of this rectangle and the area of the, let me change color, to illustrate the idea, area of the bigger rectangle, this rectangle. So the areas of these two rectangles, the sum of the areas is our answer, right? Velocity times time is distance, right? Even physically, the formula, the distance, or not distance, like the formula that we understand, what you call intuitively, is that velocity is distance over d for derivative also. So let me use the notation s, which is more common for in physics. Distance over time. So the distance is velocity times time, right? So that gives us the distance here, the area. Okay, this is 15 and the total is 25. So your answer in this case will be 15 times 2 plus, because the length of this interval is 2, and then 25 times the length of the other interval is 3. 75 plus 30, 105 meters. Okay, the unit is meters. Okay, Now, the next problem. Given the graph of a positive velocity of an object moving along a line, what is the geometrical interpretation of its displacement on the interval? Okay. The geometric interpretation of the displacement is the area under that graph between x-axis and that. If this is the velocity, and that's time axis, then this is the displacement. Okay. Now, please understand that the word positive velocity here. See, if the velocity becomes negative, then you have to take the difference of the area. Okay, probably it will come up later, but let me illustrate with a diagram. Suppose, your velocity was positive for some time and then it became negative, like that. Then you have to consider this. You have to take this area A1, this area A2. This will be the distance in the forward direction. This A2 will be the distance covered in the backward direction because the velocity is negative. Okay, so your net displacement in that case, net displacement will be A1 minus A2. Okay, in other words, the area which is below the x-axis is counted as negative area. And as we said, it like the meaning of that negative area, it's not like the area is negative, like we, not, if you just say that, it may not be meaningful. But when we understand that area in this context represents the displacement from the initial point, then the negative makes sense, right? When we talk about displacement, not distance, displacement, then there is a question of direction, so positive direction and negative direction. So the displacement will be A1 minus A2. However, if the question is asking for distance, the total distance traveled, like, if I take my car from here to the college and back to home, displacement is 0. But the distance is twice the distance between my home and college, right? So, if the question is about distance, then we would say A1 plus A2. If the question is about displacement, then A1 minus A2. Okay? So here it is asking displacement. All right. I'll erase this all now and go to the third problem. Velocity in feet per second of an object moving along a line is given by f of t. Oh, okay. In the previous question, one quick thing, I didn't notice the interval thing earlier. So that is like, suppose it doesn't have to be always from origin. Okay. Just wanted to highlight that, like that. If it is from A to B, then this particular, so that is the distance, displacement between the time A and B. Okay. So not from the beginning, but the displacement of the object between time A seconds and B seconds would be the area under the curve from A to B. Okay. Now, for question 3, the velocity of an object moving along a line is given by that from 0 to 8. Oh, okay, diagram is given below, it seems. So I'm going to scroll down. Divide into n equal to 2 sub-intervals 0408, and on which assume the object moves at constant velocity equal to the value of b evaluated at the midpoint. Okay. All right. Now, I will solve this problem, but let me talk about the concept here. Now, this is, in problem number 3 here, is an illustration of that concept of Riemann sum, right? Hope you remember Riemann sum from our discussion in the previous video. What was the idea of Riemann sums? If you want to estimate the area under a curve, right, you divide the interval on which you are estimating the area into subintervals, and then in each subinterval you take a rectangle. The height of the rectangle you choose with some logic. Okay, you can sometimes always choose the left endpoint, sometimes always choose the right endpoint, sometimes make it random, any random point in the interval, and the value of the function at that random point will be the height of the rectangle, and so on. Okay, so basically you have to choose one point on that interval, and in, like, for comparison sake or for simplicity, we try to be consistent. Always left point endpoint, always right endpoint, or always the midpoint, or always a randomly chosen point. Okay, that is also consistent, right? In every interval, just use some software and choose a random point. And then at that point, you look at the height of the function, and that would be, and then you assume that that's going to be the value of the function for the whole interval. And that's how we get these rectangles and we add up. And we know if we have more rectangles, we'll get a better approximate of the area, right? That illustration, that concept is going to be illustrated here. If you look at part A and part B, it is asking for first two intervals, two subintervals, and then four subintervals. And then we'll see how close, which is more closer to the actual answer. I will discuss that once we are there. Okay. Now, let me scroll down. Okay. So the diagram is already given to us here, and a lot of work has been made easier for us in this problem. Okay. Later we will do other problems where we will ourselves do this. So for this subinterval from 0 to 4, the midpoint is chosen, okay, for the height of the rectangle. So that's the height of the rectangle. So the answer here would be 40, the height, times the interval length is 4, plus for the interval from 4 to 8, the height is chosen to be this value here, which turns out to be 70, and then you will do times 4, right? So one of the advantages of choosing intervals of equal lengths would be this times factor, the delta x. Okay, in the notation in the theory, that will be same for all the subintervals. As a result, you can just add the values of the functions and then multiply by a single delta x. So I can say this is 40 plus 70 delta x, which is 4. Okay, so that is going to be 440. So that is going to be 440 feet according to the units given. The total distance traveled by that object, from 0 to 8 seconds is 440 feet as approximated by two subintervals. Let us see what happens when we take four subintervals. On the right side here, so like before, let me add up everything and multiply by times 2. Because each subinterval is of now length 2, each subinterval has length 2, and there are 4 of them, right? Okay, and what are the heights? In the first one, 30, in the second, 50, in the third, 80, in the fourth, 40. Okay, so 80 plus 80, 160, plus 40, 200 times 2, 400. Okay, with 8 subintervals, the estimated area is 400 feet. I want to see if there is a second. No, that's all is in the question. Uh, I was going to say we are going to discuss which is the more accurate, right, between these two. Now, our theory tells us that the second diagram, in general, okay, the second diagram or the second calculation should be more accurate. But how do I verify that? Here is how I will justify, okay? And this is a little extra concept for you. Some of you might have heard about this. There is this technique of finding the area of irregular objects, right? Which is you count how many squares are included in it. If the squares are fully included, let me count them. Okay. For example, in this diagram, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. See, colored or not colored is not, doesn't matter, okay? Under the curve, what is the any squares that are under the curve and fully included, I'm counting them. 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Okay, so I can say these are the squares which are fully included, right? So 32 of them. Then we count those which are included more than half. Okay, and we ignore the ones which are included less than half. So the idea being that, if you count the ones that are included more than half, but ignore the ones that are included less than half, on an average, they should balance out. So the positive error and the negative error would balance out. That is the idea. Okay. So which ones I will count? Let me count one. I'm writing in a different color, one here. And I will not count that. I'll just put a dot. The this part, let me count. Okay. And that, let me not count that. Let me count this. Now, sometimes it's a question of judgment. Okay. So I will count this. I'll count that also. 4, 5. I will not count it. I will not count it. Count this. 6. Like if it is covered more than half, if that square is covered more than half, count it. Not that, not that, but this. Okay. So let me see how many I missed. 1, 2, 3, 4, 5, 6. So there are 6 squared which we did not count, which are covered less than half. But there are 7 squares which are covered more than half, and we counted them in. Okay. Anyway, that is the best, like, again, it's not the exact, but much better approximation. Okay. That is as, I think, as good as you can get in terms of approximation. So you have totally 32 plus 7 equals 39 squares. Now I need to multiply that 39 by the area of each square. Now what is the area of each square? The scale here is 20. So that's 10 for one box. Okay, the height is 10 and the width is just 1, right? So times 10, 390. Okay, so 390 feet is a very good approximation of the actual area under the curve, the actual distance traveled. And 400 is closer to 390 than 440, right? Okay, so in a way, we see that increasing the number of rectangles gives you a better approximation in the dimension. Okay, moving on. That was a fun exercise actually. Let's see. Number 4 sounds similar to me at the outset. Divide into 3 subintervals, and on each interval moves constant velocity. The value, okay, left endpoint. Okay. Now, again, this is another illustration. Probably I'll not do it, okay, because we have done the one before. The only difference from the previous problem to here is now the height of the rectangle in each subinterval is chosen to be the left endpoint. Okay. I will do one such problem later where the diagrams are not given, so we will construct ourselves. See, in each case, for each rectangle, let me erase that actually. Here, this is the height for the first rectangle. This is the height for the second rectangle. This for the third rectangle. So in each interval, the left endpoint is the height. The value of the function at the left endpoint is the height. Okay. So this is with 3, that is with 6. And actually, visually, it is very easy to see which one gives you better approximation. Okay. And by the way, in this case, both of them are going to do an underestimate. I had talked about that concept also in the theory, the first introduction video. Okay. These, the areas of these rectangles, when you add up, they will underestimate the area clearly, right? Because you are missing out some things. Okay. And that will be the case whenever you use left endpoints for an increasing functions. And I'll make note of that here. Okay. So that's the concept you might want to remember. Using left endpoints for height, okay, of the rectangles in an increasing function implies what? Underestimation. Think of that. Okay. If you had used right endpoints, you would have overestimated. For what? For increasing function. That's important. Okay. So it doesn't depend just on one factor. There are two factors at play here. I think that was the main thing I was going to say. Left endpoints, increasing function. That combination makes it underestimate. If you change one of them, it will become overestimate. Okay, so there are 4 different possibilities, right? Now, if a function is both increasing and decreasing, then they will tend to balance out. Okay. Moving on. I think the next question is asking you to do right endpoint as I suspected. Okay, so a similar exercise, but with right endpoints, and the function is both increasing and decreasing here. Okay, so even without a much more careful observation, you cannot say whether it is going to be underestimate or overestimate. Okay, and you can actually count how many squares are overestimated and how many are left out. But I mean, because the function is both on the whole interval, it is first decreasing and then increasing. So you cannot guaranteedly say it is underestimate or overestimate without more closer observation. Okay. Here you could directly say it is going to be an underestimate because the function has a constant behavior of increasing on that whole interval. Okay. Here you cannot say. But you are using the right endpoints. Okay. Let me focus on that concept. See, for the interval 0 to 2, you are using the value at 2 as your height. For the interval from 2 to 4, you are using the value at 4 as your height of the rectangle. Okay, and from 4 to 6, you are using the value at 6 as your height of the rectangle. So that is using the right endpoints. And then add the areas of the rectangles, you get the estimate. Okay. Let's see. Is this also asking for a diagram? Okay, but let's read the question. The velocity is given here into 5 subintervals. On each interval, assume the object moves at a constant velocity evaluated at the left endpoint. Okay, so this one is asking you to do both. First with the left endpoints, then with the mm, uh, repeat with the right endpoints, and then repeat with the third with the midpoints. Okay, and estimate. So basically, we'll get different estimates, by using different endpoints, and I can tell you what will happen. Okay, I'll not solve it because I think it is going to be a repetition, but the concept. Okay, what will happen? Which one will be underestimate? Which one will be overestimate? And which one will be difficult to say? Let us discuss that. All right. Because this is an increasing function, using the left endpoints. For example, if you are doing 5 subintervals, your first interval will be from 0 to 2. Okay. In that interval, you use your left endpoint, then that means this is the rectangle you are going to consider. So clearly you can see from 2 to 4, you will be using this rectangle. And there are parts you are going to be missing, right? This part is going to be missing, that part is going to be missing. So the left endpoints will give you underestimate. What will the right endpoints do? I'll change color and try to get the rectangle. For the right endpoint, for the first interval from 0 to 2, that will be your height. So this will be the rectangle you will consider. And from 2 to 4, the right endpoint is at 4, so you will consider that rectangle. So you can see you are going to count some extra squares, or extra area. So that will be an overestimate. Left, underestimate. Right, overestimate. Okay. And let me erase that and discuss the midpoint. Okay. Now, if you take the midpoint, for example, here, you would be taking that between 0 and 2, that will be your height. So your rectangle will be this. Now you're missing some part here. Sorry, you're counting some extra, but you're missing something, right? In the next one, or let me try 6 to 8, let's say here, that will be the height, like that. And you can again see you're missing something. You're missing something here, but you're counting some part extra here. Okay. And so you can see the it will be actually more accurate. Okay, because you're not always underestimating, you're not always overestimating. In each subinterval looks like you are going to miss something and count something extra. They will tend to balance out to some extent. So among the three, left, right, and the midpoint, as your choices for the height of the rectangle, my general guess would be that the midpoint ones would be the most accurate to the actual area. Okay. It's not going to be exact. So at the end, it is going to be a small amount of underestimate or overestimate, but it would have been balanced out to a large extent. Okay. Question number 7. Let me discuss that. Now we are going to like do things that are diagrams are not given to us. Suppose you want to approximate the area of the region bound by the graph f of x equals cos x and the x-axis between 0 and pi over 2. Explain a possible strategy, right? So we know at this point, later on, we will of course do the antiderivative using formula and get an exact area. For now, our strategy will be to use the interval method, the graph of cos x between 0 and pi over 2 is going to look like that. Pi over 2 here, 0 here, that's 1. And then your strategy will be, you will take maybe, you can take boxes of length 0.1, 0.2 like that, and divide it into subintervals. Uh, if you want to use standard angles and not use a calculator, then go with pi over 6, pi over 3, and pi over 2. Okay, those will be 30 degree, 30 degree, 30 degree intervals, right? And then in each interval, you choose either the left or right or midpoint. I would recommend midpoint. Okay, like from the previous graph, we know midpoint would be a better approximate, right? So in each interval, choose the midpoint as the height of the rectangle. That for the first one, this for the second, let's say here, so that's for the third. And add up, then take the sum of those rectangles, and by when you add up the areas of those three rectangles, you'll get an approximation. Okay. um oh, okay, then you have to use the calculator because you are going to use the value of cos at 15 degree. So for the first one, you will do cos pi over 12. Here this is between 30 and 60, that's 45 degree. Okay, for the second one, you will use cos pi over 4, and the last one is between 60 and 90, 75 degree. So there you will use the value of cos. No, 75 is what? 5 pi over 12. Okay, and times the interval, like add up these three things, plus plus, and then multiply by the width of each interval, which is pi over 6, times pi over 6. That will be your approximated area. Okay, all right. And if you want to make it better, of course, divide it into more intervals. Explain how Riemann sum approximations to the area of a region under a curve change as the subintervals increases. I think we talked about it enough number of times. It becomes better, right? The approximation becomes better when you increase the number of subintervals. Okay, approximating area from a graph. Use left and Riemann to obtain different ones. Okay, so this is a decreasing graph, so I can discuss here. Almost decreasing for most of the part. Okay, not everywhere actually. Here and here it is increasing, but mostly it is decreasing. So using the left endpoints will give you an overestimation here. Okay, and using the right endpoints will give you an underestimation. For example, between 1 and 2, here actually it will balance out because there is some part is increasing and then it is decreasing. This might be more or less accurate, but after that, this is an overestimate because you are using the left endpoint as your height. This is an overestimate, right? And that's going to be clearly an overestimate. And here again, overestimate. Okay, so the left endpoints would be these rectangles. Oh, I think I did not do this correctly. Here, not that. Okay, I think others are correct. Yeah. So these are overestimates here, mostly overestimates. So if a function is decreasing, then the left endpoints give you an overestimate, right? Okay, that's the idea. This is an increasing, so you'll can compare and contrast. Okay, I think that's enough for the discussion on theory there. Let us move on to some other examples. Okay, approximating displacement is given by 3t square plus 1. Okay, that formula graph is given, divide into subintervals and in each interval. Okay, so this will require us to construct a table and do it. Oh, okay. So I am taking a lot of time making these videos. I'm going to make another video. Okay. Now we are going to be doing some problems, where not either like function is not the usual function, or hopefully later not every time diagram is given. Okay. I'll make one more video on solving these problems. I'll see you next.